This is part 2 of the accumulation function fundamental theorem of calculus notes. We just did p of x up above. Now we're going to continue with q of x. It's really pretty much the same problem, just some different numbers and a different function here. So if you understood what we did in the first one, feel free to skip this one or skip to the end and gather the results. Otherwise, we'll just go through this. So q of x is the integral from -1 to x of g of t dt, where g is the function that we have here. So let's just jump right in and let's find q of -3. So that's going to be the integral from -1 to -3 of g of t dt. And we can do this a couple of different ways. In the example above, I switch the bounds. In this case here, let's just go ahead and leave them the same. I do know, since I'm going from -1 to -3, we're moving to the left, my area will be negative. I'm also going to do this one because our slopes here are -1 and +1. We have some nice shapes here that we can just work with. So I'm just going to count squares. I have 1, 2, 3½ squares. So my area is going to be -7/2. If you want, feel free to leave it as -3½ or 3.5, whatever you prefer. Let's move on to q of -2. So that's the integral from -1 to -2 of g of t dt. So now from -1 to -2, we're gaining back these two blocks that we had over here that we were negative of. Now we're just -1½ so our integral is going to be -3/2 here. Q of -1 is the integral from -1 to -1 of g of t dt. And because the lower bound and the upper bound are the same, the area is just going to be 0. Q of 0 is the integral from -1 to 0 of g of t dt. So now we have this area from -1 to 0. So again, that's just a triangle. That's half a square. So the area is just going to be +1/2. Q of 1, the integral from -1 to 1 of g of t dt. So we're going from -1 to +1. Well, in this case here, I have a +1/2 square there. I have a -1/2 square here. Those will cancel each other out, giving us an accumulated area of 0. Q of 2. Okay, so we're just going from -1 to +2. And again, since we're accumulating, we know that the area from -1 to 1 is 0. So all I need is this area here, which is going to be -1/2. And then Q of 3. We'll just be adding on this +1/2, which will take us back to 0. Okay. So from there, we can go ahead and plot this curve. -3, we're at -3½, so -3, 1, 2, about 3½ would put us here. -2, we're at -1½. At -1, it's 0. At 0, 1/2. At 1, we're at 0 again. At 2, we're down here at -1/2. And 3, we're back at 0. So my curve, if I were to connect these, I get a graph that looks like this. And then just as our results were up above, that Q is increasing wherever G is positive, and Q is decreasing wherever G is negative. Okay. So we start looking at this next part here. Why is this connection true? Okay. Well, let's first of all start with, if I have my graph of f in the very, very beginning, let's just assume that this function is the derivative of some other function we're going to call big F here. Okay. So the derivative of big F is little f here. Then P is the integral from 0 to x of f of t dt, again referring to the very first example. If we integrate this, then this will be big F of t evaluated from 0 to x. Because again, we're asking this. This function here is the derivative of what? And we just said up here we called it the derivative of big F. Now use the fundamental theorem of calculus that says when you evaluate a function from 0 to x, that we plug in the upper bound minus we plug in the lower bound. And so now I'm going to go ahead and we're going to derive this since all of these are equal. That means p prime would be the derivative of the integral from 0 to x of f of t dt, which will equal the derivative of this, which is going to equal the derivative of all of this. But notice this, the derivative of f of x is little f of x minus the derivative of 0, or f of 0. Well, f of 0 is just a constant, and the derivative of a constant is 0. So we're subtracting 0 in this case. So the conclusion is that p prime is equal to little f of x. So I'm going to go ahead and finish by just flipping over to the second page here. And this is the big result from that first page. So let f be a continuous function on the closed interval a to b. Then the derivative from anything from a to x of f of t dt is equal to f of x. Okay? In the next video, I'm going to go ahead with these examples. We'll talk a little bit more about the findings, and we'll go from there. Thank you.